So time to discuss aging in survival analysis. So what do we mean by aging and why is it so important to discuss? Let us see. So what do you mean by aging? What is aging? Do you mean this? That a child is growing up, an infant, then a boy, a little boy, then a teenager, then a man, and then an oldie. So what do you understand from this picture? So is getting old, what is that what we mean by aging? So how can we use it in survival analysis? How this concept is important in survival analysis? So let us see. So what is the meaning of aging statistically? How do we measure or how do we define aging? So by aging we mean the procedure of getting old. So this is a literal meaning. So for non-living things, how do we measure it? So we would say it means wearing and tearing. So especially mechanical items, or even your electronic items these days, your mobile, your laptops. Right now I am having serious issue with the charger of my laptop. So why? Because the cord is a bit loosened up, so it's not getting connected properly to the laptop, and so as a result I'm unable to charge the laptop. So why is it happening? Because of the extensive usage of the charger or the laptop, and so the cord is it's a mechanical failure, and so this has happened because of the extra usage. So some wearing out is happening with the cord. So this is what we mean by aging. So it can happen with living people. We know it is aging. You know the concept. But for non-living thing, how do we define it? So for certain items, it looks like there is no aging. But if you watch carefully, you will notice that most of the items, even though the wearing out rate is slow, it is still there. Wearing out is still there. So aging is still there. So the concept of aging plays an important role in the choice of models for the lifetime distributions. It is particularly useful in engineering applications to model the lifetime distributions of units subjected to wear and tear or shocks. Because certain items they undergo a lot of stress. For example, the brakes of your vehicle, whether it is a two-wheeler or a four-wheeler, any vehicle. If you consider brakes, yes, they are needed. They are used a lot extensively, especially in Indian roads. They have to be used. So can you say that they are subjected to wear and tear and shocks? So yes, it's kind of true there. So this is what makes it important to study aging. Because if I want to go for a particular brand, how am I going to choose? So it will matter how much or how long the item is going to last. So how the item means, what is the chance that that item I'll be able to use that item properly? It will be usable for a certain period of time. That is a very common question when you go for purchasing something, isn't it? You want to know how much is the reliability. Means what? You want to know what is the chance that it will be working properly even after say 5 years. If it is a say mobile, if it is a laptop, still you would want to know how much is the means technical details will be there, definitely there, like configuration and other stuff. But at the same time you would want to know how much good the hardware is, because certain laptops you might have heard ki they last long, means their durability is more. So again the concept durability. So you might have heard the word, but can we define it statistically? Isn't it? Because finally we are studying it through the statistical point of view. So similarly, we should be able to define the process of aging through statistical point of view. So how do we define it? So there are three major categories in aging: no aging, positive aging, and negative aging. So let us have a quick introduction to all these three. So what is no aging? Looks very hypothetical, isn't it? You might feel that how is it possible? How can it happen? No aging means what? How do we define it? No aging means age has no effect on that item, right? How can you define it in simple manner? There is no adverse or positive effect of age on that item. If that is the case, then there is no aging, right? You would say that. You may ask, how is it possible? Are there actually in life, do we come across such items? So I don't know how many of you have tried to buy utensils. But if you go to buy utensils, especially stainless steel utensils, you might have heard this from the seller, ki the item is going to last longer than you. Means a human life is not as much, it won't be as much as a stainless steel item. If it is a good quality stainless steel, you might have heard this. I have heard it from us. Whenever a seller tries to sell stainless steel item, he utters this, ki the item is going to last longer than you. So you feel happy, yeah, till I am alive, I'll be able to use it, or it will be in a good condition. And more or less it is true. It remains in a good condition unless we expose it to a certain drastic situation, like if something is run over from that item, then it is bound to break. So can we safely say that when it comes to the lifetime of a stainless steel item, can we say that it has no aging? So let us come back to the point which we were discussing. We are discussing no aging. So let us try to define it statistically. So, suppose an item or a unit is of age t, then suppose the residual lifetime t. Here this there is a change in notation. This should be t suffix small t, capital T suffix small t. So please note this change. So if the residual lifetime is this tt with f bar t as its survival function, then what? Then what do we mean by no aging? So we are already considering a used item, right? An item of age t means it was already of age t means what? When you say an item is of age t, means do you mean that it was manufactured and kept aside and it was not used? Then will it matter much? Then there will be the concept of shelf life. So all these things we are not going to consider. By age t we mean that the item was produced and it was in use for t units of time. So by this we mean that the item is of age t. So there is no question of shelf life. So by what do we mean by no aging? So by no aging we mean the unit has not aged at all. Means what? Age has no effect on the residual lifetime of that unit. So it doesn't matter whether the item is 1 year old or 2 year old or 10 year old. It does not matter. Means what? How? What do you mean by not matter? So it means that whether the item is 1 year old or whether the item is 10 year old, it won't affect the rest of the life of that item. It will behave as if it is a fresh item, a newly produced item, right? A used item or of unit, a used unit of HT is as good as a new unit, isn't it? Again, isn't it applicable to stainless steel items? Can you find any more such real life situation except exponential distribution? Because exponential, we know it has constant failure rate. So it is as if the item having exponential lifetime will be as good as a new item. So that is there. But in real life, have you found lifetimes of certain items to be following exponential distribution? Or you feel intuitively that that item has no aging? So if you find such item, do drop a message to me. Your messages are really welcome. So a used unit of HT is as good as a new unit. So how do I mathematically define it? So I would say the survival function, let us consider this first definition. The survival function of an item of HT is same as the survival function of a fresh item, freshly produced item. Means item having age 0. So here F bar denotes the item of age 0, means the instantly produced item having age 0. And here F bar t denotes the survival function of an item of age t. So when t is equal to 0, I am simply denoting it by F bar. That is what we mean. So this is survival function of a fresh item and this is a survival function of an item of age t. So when both are same, you would say that there is no aging. So this is both the sides are functions. So when you say that two functions are same, when they are same, they take the same values for all possible arguments. So if that is the case, then the functions will match. So let us try to plug in the value of this f bar t. What is f bar t? But basically survival function of an item of age t. So how do you calculate it? So f bar x is basically probability that an item lasts for an item has already lasted for t units of time. So given this fact, what is the chance that the item will last for x more time units? So if you solve this carefully, you will get finally f bar t x as f bar at t plus x upon f bar at t. So this equation gets simplified to f bar x is equal to this. So if you again simplify this, you get f bar x into f bar t as f bar t plus x. What is the meaning of this? So it means that the probability that an item, a freshly produced item, means an item of life 0. So an item will survive for t plus x units. This chance is simply the product of the chance that it will survive for x units of time and the chance that it will survive for t units of time. So it is product. So it means there is nothing interdepending on each other, means there is, it does not matter. I am simply breaking up this interval, isn't it? T plus x I am simply breaking up into t and x. So this is an interesting equation. So exponential distribution is the only continuous distribution which fulfills this equation. So this equation is called as Cauchy functional equation. This equation they call it as Cauchy functional equation. And one can easily prove that exponential distribution is the only continuous distribution which satisfies this equation. So this is what we mean by no aging. Now what else can be said about no aging? So electronic items, light bulbs, etc. often exhibit the no aging phenomenon. So do you think that light bulbs? So see, till warranty period it is as if the failure rate is constant. So you can safely say that the exponential distribution can be applicable. See, exponential distribution, even though the range is 0 to infinity, you know that the distribution's survival probability or survival function for that distribution reaches 0, almost 0 value after a certain point, isn't it? So it is possible that that point is nothing but the warranty period. So even though it looks like it is difficult to have exponential as a model for light bulbs lifetime, but after a certain tweaking you can always do that. So these items do not change properties with usage, but they fail when some external shock like a surge of high voltage comes along, right? It happens with many electronic items. So because till that external shock the item has equal chance of survival, so you can say the failure rate is constant for that time period, and so you can safely say that there is no aging. So since a used component is as good as new stochastically, so this is another way to define no aging. So there is no advantage in following a policy of planned replacement of used components known to be still functioning, isn't it? Had you thought about this as a effect of no aging? There is no advantage in following a policy of planned replacement. Why? How can you plan replacement for certain item whose failure rate is same? Since the old item is going to be as good as the new item, there is no need to have a replacement policy for the items having no aging. So in statistical estimation of mean life, percentile, survival function, etc., the data may be collected consisting only of observed lifetimes and the number of observed failures. The ages of the components under observations are irrelevant, isn't it? If the item has no aging, then when it comes to estimation, the data of actual lifetimes won't be that much important, isn't it? How many failures have been observed and how long the failures were observed, that much only is going to matter, because the old items, so suppose an item survived for 2 years, an item survived for 4 years, so is it going to matter much when it comes to estimation? Isn't it? So these are all the effects of no aging of the items. Now let us quickly go through the basic terminology. This, I think, hazard function, you are already familiar with hazard function. So it is defined as the instantaneous failure rate. So what do we mean by instantaneous failure rate? So it means that suppose you have an item of age t. So the item has already survived for age t. So t is greater than small t. Means what? What is capital T? Capital T is the lifetime of that item. So item of age 0, lifetime of an item of age 0 means lifetime, but not the residual lifetime, but lifetime you are counting right from the beginning. So that lifetime you are denoting by capital T. So if the item has already survived for T units, what is the chance that it will fail at the next instant? So how do I say at the next instant, at that instant T? So I will have a really small interval from T to T plus H, and I'll consider failure of that item in that interval, and then I'll try to reduce the interval as much as possible. So the hazard function is nothing but the instantaneous failure rate of an item of age t. So hazard function at time t will be defined like this. So if you simplify this, you will notice that this gets simplified to f bar t minus f bar t plus h upon h into f bar t. So as h tends to 0, this except f bar t, the rest of the thing actually gives you the PDF, means the derivative of CDF, and so it will be the PDF provided that the PDF exists. So the hazard function will be simply the ratio of PDF upon survival function. So now the next term is also important, that is cumulative hazard function. Means what is the, see, because hazard function in a way indicates failure rate at that time. So it will also matter how much was the failure rate till that time. So this concept or this idea is represented through cumulative hazard function. So capital RT will be integration of this hazard function simply. So if you try to simplify this, you can easily notice that, means put this RU here and do some mathematics, and finally you will get the survival function as exponentiation of the negative of cumulative hazard function. So this expression is also important. Then one more expression which is, or the term which is important, is mean residual life. Notice that very rarely we come across fresh items. Most of the time we come across used items. So won't it matter how much remaining life on an average will the item has? This will be a point of interest. So this is demonstrated through the concept of mean residual life function. So what is it? It is simply the expectation of this variable t suffix t. This capital T suffix t indicates the residual lifetime of an item of age t. So it will be 0 to infinity f bar t u du. How do we get it? So by the definition, that expectation can be integration of survival function. You might have studied this while you studied probability distributions. So this will be simply integration of this. Substitute the values, and so this, the usual notation for mean residual lifetime is LFT, or one more notation which is very popular is mu t, mu bracketed t. So this can also be used. So this is an important concept. We are going to need it several times. So enough about no aging and the terminology which we needed. Now let us come to positive aging. What is the meaning of positive aging? It means that the age has adverse effect on the residual life of the unit. Means what? So it means that as age increases, the aging also increases. So what do we mean by that? So if I say let us talk about the, in terms of the failure rate. So if you consider failure rate, then the failure rate at the age say 10 and the failure rate at the age 20. So the failure rate at the, if the aging is positive, then it will mean that the aging has adverse effect. So the failure rate at age 20 will be definitely more than that at age 10. And this will be applicable to all the ages because of the positive aging. So you can say that the failure rate is increasing function. And so one way to judge or to measure whether the aging is positive or negative or no aging. So one way to check whether there is positive aging is through failure rate. So if the failure rate is increasing, in short, if it is IFR, then you can say there is positive aging. Then another way to check the positive aging is increasing failure rate average. So what will happen if your failure rate is increasing on an average? So what do we mean by IFRA? We will be discussing it in more details in the next lecture. So this is again another way to check the positive aging. But this I think you will understand here. So I will explain this here itself in this lecture. So NBU. So what is NBU? So NBU is new, better than used. Means an new item will always be better than a used item. So if that is the case, then there is positive aging. Then it will indicate in a way that age has had an adverse effect on the item. Then one more way to judge is new better than used in expectation. So another way, just like you have IFR, then you are going for expectation of on an average, what is happening on an average. So IFRA, similarly NBU and NBU are connected with each other. And the last way is the last term is DMRL. So what is DMRL? So it is decreasing mean residual life. So if the mean residual life function is decreasing, then means as the age progresses, if the remaining life, average remaining life of the item goes on decreasing, then it is again will mean that there is positive aging. So this is, I have tried to summarize the concept of positive aging here through this slide. So now similarly we have negative aging. So it means the age has no adverse effect. So just whatever you imagine for positive aging, now imagine the opposite of that. So that will be negative aging. Means what? So earlier you had failure rate increasing, now it will be decreasing. So it's like older the better. You can in two words you can explain or you can describe negative aging is the older the better. So if older the item, the better it will be. So it could be a quality aspect, it could be a usage. Means here we mean not quality aspect, here we mean the longevity of the item. So older items will have more residual life than the new item. Can this happen? Do you think it is possible? What kind of items will have negative aging? Have you ever heard about negative aging? Are there any items which have more chances of failure when they are fresh and their chances of failure decrease as the age increases? Isn't it? So what do we mean by no adverse effect? So by that we mean that in fact aging has a better aging has a aging increases the residual life of that item. If that is the case, then that will be called as negative aging. So there are similar to positive aging, there are various ways to define negative aging. So it can be defined through decreasing failure rate. It can be defined to DFRA. It can be defined through NWU. So what is NWU? So new is worse than used. New worse than used. So NWU, then NWUE. So new worse than used in expectation, and IMRL is increasing mean residual life function. So these are 5 different ways in which negative aging can be checked. So here we are at the end of the presentation. So more about all these things I'll discuss in the next class.